9.11 practice problems. The diagram opposite shows the apparatus used for the electrolysis of copper 2 chloride according to the chemical equation given. Which of the following mathematical expressions could be used to calculate the current required to produce 0.125 moles of copper within 1 hour? So we know that our overall equation is going to be that our current, which is I, is going to be equal to Q over T. And this time is in seconds, and the Q is going to be the moles of electrons times Faraday's constant. And we have those expanded out here. So we are dealing with 1 hour, so we can go ahead and eliminate option choices B and D as they are just divided by 1, and we are in seconds, not hours, so that would leave us with option choice A and C. Then the differential between these two, we can see that Faraday is the same in both, and that we can see the overall moles of copper being the same in both, but not the number of electrons. So in copper 2 chloride, copper has a charge of positive 2, and so that means that we had to give it 2 electrons per 1 copper, so 2 times the overall moles of copper times Faraday divided by our time in seconds is going to be our answer choice, and that is answer choice A. The diagram above shows the experiment setup used to electroplate a small object. A current of 0.8 amperes is supplied to silver nitrate for 30 minutes. Which of the following equations can be used to calculate the approximate mass of silver deposited onto the object? Okay, so overall we need our mass, and our mass is going to be equal to the Q times the molar mass of the silver nitrate divided by the overall number of electrons, and that being multiplied by Faraday's constant. So, looking here, I need to be dividing by Faraday, and I can see Faraday in 3 of the 4. So I can go ahead and eliminate the option choice B that doesn't include Faraday at all. Now looking here, I can see that N being the number of electrons should be 1, since silver has a defined charge of positive 1, which means that we gave it 1 electron. So it should just be Faraday down at the bottom. The 1079 is the molar mass of silver nitrate, so that doesn't quite make sense. So next up, I just need to look between these two answer choices and see what's going on here. So I have my Q value being equal to my current, which is the 0.8 amperes, and that needs to be multiplied by my time, which is 30 minutes, and there are 60 seconds in every minute. So we could have said 1800 seconds, but they obviously did not do that. Instead, they had 30 minutes times 60 seconds per minute, and so that would be answer choice C. Answer choice D leaves my time in minutes, and so that is not going to be my answer choice, since that is an inappropriate unit for the time value there. The vanadium-lead galvanic cell in the diagram opposite initially operates under standard conditions according to the net reaction shown in the table below. The cell operates for 1 minute at a constant known current. Which of the following mathematical relationships would be the most useful for determining the change in the mass of my electrode after 1 minute if the cell's operation without having to use a balance? So if I want to be able to determine the mass, I need to first use an equation that will allow me to directly relate mass to that thing. And that is not going to be my delta G values there. Okay, I don't have any of those pieces of information. That's not particularly helpful. And this as well, not going to be particularly helpful. I don't have my Q value. I don't have lots of this information. It's not going to really give me the information I need. However, option choice B, where we have that I is equal to Q over T there, we are going to be able to utilize that to find my mass, since again we just used that the mass is equal to Q times the molar mass divided by the number of electrons times Faraday's constant. And so since we have all the information that we need here to find this equation's value and find our Q value, we can get to our mass. So answer choice B is going to be my best answer choice. In the electroplating of nickel, 0.2 Faradays of electrical charge is passed through a solution of nickel to sulfate. What is the mass of nickel deposited? So we're going to go ahead and use that same equation. M is equal to Q times my molar mass divided by the number of electrons there times Faraday's constant. And so our Q value, we need to go ahead and convert out of Faraday's into coulombs. So our relationship between Faraday's and coulombs is that there is 96,485 coulombs per Faraday. And so that times our Faraday of 0.2 value. Gives me 19.297, and that is our value for Q. And then our mass of the nickel to sulfate. Sorry, not the molar mass of nickel to sulfate instead of just the mass of nickel. That's the compound of interest. And so the nickel weighs 5869. And so 19.297 times 5869 divided by my number of electrons. This is nickel 2, so that means that there's 2 electrons, and then that times Faraday's constant, which is that 96,485. Go ahead and plug that in. And I get 5.87 when we round to the correct number of sig figs, which is answer choice B. An electric current of 1 ampere is passed through an aqueous solution of nickel 2 nitrate. How long will it take to plate out exactly 1 mole of the nickel metal, assuming 100% current efficiency? And then we have that 1 Faraday is equal to that many coulombs and that many electrons. We're going to need a couple of equations here. We want eventually to be able to use that Q is equal to I times T. However, I first need this Q value. And so that means that I'm going to have to utilize what I do have, which is the amount of electrons and Faraday's constant. So I'm going to initially use that Q is equal to my number of moles of electrons times Faraday's constant. This is nickel 2, and we just want 1 mole, so that means that we are going to be dealing with 2 moles of electrons times Faraday's constant of 96,500. So And then we can go ahead and solve for T. So that means it will be Q divided by I. And it is 1 ampere, which means that we're just dividing this by 1. So our time in seconds is this divided by 1, which is the same thing, and 193,000 seconds is going to be my answer choice, which is option choice B.